We will quantize a co-adjoint orbit of SU2 and we'll answer the following question. Given a symmetry group G, find a quantum mechanical system whose Hilbert space is an irreducible representation of that symmetry group G. So we'll first do this for the group G equal to SU2. It's a Lie group with a Lie algebra, which is also SU2. So it's the group of three-dimensional rotations. You can also think of it as SO3 extended by a Z2. And it acts naturally on a two-sphere by rotations. A very important thing is that the action is transitive, meaning that any point can be mapped to any other point using the rotation group. So this gives us a first element of what we need to answer the question, because clearly we want to quantize a phase space which has the dimension of the irreducible representation Planck cells. So cells of size the Planck constant, because each cell of size h gives rise to one state in the Hilbert space. And since we need dimension of the irrep number of states, we need the dimension of the irrep number of cells in our phase space. It's the first requirement. And the second requirement is because it's an irreducible representation, you have to be able to map all cells to all cells. And that is precisely what the transitive action does. If I have a cell here, I can map it to any other cell. So the irreducibility classically translates to the transitive action. Now for SU2, the dimension of an irreducible representation is 2j plus 1, where j is called the spin of the irreducible representation. And therefore, the volume of our phase space with transitive action has to be 2j plus 1 times h, which is nothing but j plus a half times 4 pi h bar, where h bar is nothing but h divided by 2 pi. So if we propose a phase space on which SU2 acts transitively, which is a two-sphere, then the volume of the two-sphere has to be 4 pi h bar j plus a half. And the volume form on the two-sphere has to be h bar times j plus a half times sine theta, d theta, wedge d phi in some standard coordinate system on the two-sphere, where this is the angle phi and this is the angle theta. Because then if we compute the volume, we find 4 pi h bar j plus a half. Now, a quantum mechanical system that has this phase space symplectic form will be the following. We take a particle that lives on the two-sphere, and it has a first order action, which is basically the pullback on the world line of the inverse of the symplectic form. So if we call our map from the world line into the two-sphere, we call the map, we go from tau, which is some coordinate on the world line, to theta and phi of tau. Then this translates into the integral of d tau cosine theta phi dot, where phi dot is nothing but derivative of phi. So if the claim is this particle action with the proper constants in front, h bar j plus a half, as a phase space S2 with the symplectic form omega, and because of the properties discussed above, it has a Hilbert space which is an irreducible representation of spin j of SU2. The fact that the phase space is two-dimensional can, for instance, be seen by noting that the momentum conjugate to phi, nothing but cosine theta. So therefore, indeed, theta and phi are in some sense canonical conjugates, and therefore we have a two-dimensional phase space. If we want to do the quantization in some more detail, we would cut up this two-sphere into cells of size the Planck volume, and we would find that we have exactly 2j plus 1 of these cells. And the way I've drawn them here, we can think of each of these cells as corresponding to a particular angular momentum in the z direction. Now, what does this have to do with co-adjoint orbit quantization? Well, we could have picked an element lambda of the Lie algebra SU2. The Lie algebra SU2 is a three-dimensional vector space. We pick a vector lambda in it, and then if we act with the group SU2 on lambda, we would have found this homogeneous space, which is precisely the two-sphere that I've been describing. So the two-sphere is the transitive SU2 group action divided by the U1 that leaves our element lambda fixed. So this is homogeneous space. Which is the co-adjoint orbit for SU2 because of the non-degenerate killing metric. An adjoint orbit, which I've just described, and a co-adjoint orbit are the same. So this is the relation between co-adjoint orbit quantization, the question of finding a quantum mechanical system with as Hilbert space one irreducible representation in the case of SU2.